Okay, thank you for introduction, Yossi. Yeah, my name is JaeHyuk Kwack. For next 57 minutes, we are going to talk about Intel performance tools on Aurora. To save my traffic, let me start my video. So, uh, so do you guys hear me now? Okay,
One
okay,
second. Okay, yes, I see your screen. Great.
okay, great. Before start talking about the tools, let me briefly talk about the Aurora system. Aurora is one of the most powerful systems in the world at the moment. So this is literally exascale system. As you can see here, Aurora system has 166 compute racks, and in total it has 10,624 nodes. It's really a big system in terms of number of nodes, number of racks, and number of network endpoint, and number of GPUs. So total GPU memory is more than 8 terabyte, and then CPU side we have more than 10 petabyte DDR5 memory and more than 1 petabyte HBM memory even on the CPU side. Then we have 64 racks of the Deus 5IO system. So it's huge system, a lot of network connection happen in the system. Each rack has 64 compute blade and then 32 switch blade. And then each compute blade has two Intel Xeon Max series processor with HBM and DDR, and six Intel Data Center Max GPU 1550 models on a node. So this is a little bit more details about the Aurora Exascale compute blade. So as I mentioned before, it has six GPUs. Each GPU has two stacks, so you can consider in total 12 stacks of GPU. And also two Sapphire Rapid processors. So you can expect there is some NUMA effect happen between CPUs, right? And six GPUs are connected through the XC link, old old fashion. And then the first three GPUs are connected to first the socket of this Xeon processor through the PCIe 5 connection. And the last three GPUs are connected to socket 1 CPU through the PCIe 5 connection. And each CPUs are connected to the four NICs through the PCI switch. In total, the node has 8 NICs, eight network endpoint from the string network. So from this diagram, you can imagine Aurora system is really huge system, and then even on the single node, single super node has a lot of different components. So two CPUs, six PBC GPUs, and then connections are very complicated to each other, right? So in order to utilize all the in order to get the best performance on Aurora, you need to understand how to utilize all the component efficiently. So for that aspect, profiling tool will help you out. So this is a list of the popular profiling tools on Aurora. I may miss something, but this is kind of the most popular thing. So again, Aurora system has Intel CPU and Intel GPU. Because of that, Intel's tools are our primary tools to measure the performance and optimize the code. So you can expect the Intel BTune is available and BTune Advisor, Intel Advisor is available. So these two tools are very popular tools on CPU side as well. And for the Aurora project, Intel has been extended those tools for the GPU side. So now you can imagine BTune and advisors are available on CPU profiling and GPU profiling, both of them. So most of the features are kind of available on both devices, device and host. And VTune Advisor is pretty popular, strong tool, but it has relatively high overhead. Because of that, it's not suitable for the large scale profiling. Again, the Aurora has more than 10,000 nodes. So in this case, we cannot expect to use VTune Advisor at that scale. So for that aspect, Intel has another solution which called application performance snapshot. It has limited required the metric collection happen in this application. As a result, the overhead of the tool is pretty negligible compared to BTune Advisor, and then it enable us to provide your application performance at scale. And also additional small and very powerful tools, XPSMI, which is somewhat similar to NVIDIA SMI or ROCm SMI on NVIDIA and AMD side. So you can see some the GPU utilization real time and also power consumption and etc. So You may be if you're a fan of the NVIDIA SMI, ROCm SMI, you can also try out XP SMI. And Unitrace is another lightweight tool from the Intel. This is a tracing and sampling tool for your application, and this is pretty popular for our machine learning developers. And also, we have another tracing tool called TAPI. This is developed by Argonne, the Bryce Widow and Thomas Eppercourt. They are major developers. And they have this tool is very also lightweight tool and available on Aurora. So in my understanding, the TAPI is because this is very lightweight tool. This is most popular tool among the Argonne Aurora users. And also HP's Toolkit from Rice University and Tao from University of Oregon also available. They collaborate with each other, with us to port those tools on Aurora system. And these two tools are available on Aurora system as well. Unfortunately, I cannot cover everything in an hour. So today I will mainly talk about the Intel VTune Advisor APS and the TAFE. So I will give you a quick introduction of those tools, and then you may start using those tools. And then if you have any additional question, we can discuss offline after this webinar. So Intel VTune is mainly it's one of the popular tools on Intel CPUs. And also it's extended to GPU. So in this talk, I will focus on the GPU features because Intel VTune has so many features, something even I cannot investigate it yet. So I cannot cover everything, but I will share several features I prefer to use. So you may have some idea about them. So GPU profiling, obviously Intel VTune for support multi-GPU system analysis because on Aurora system we have 6 Fontainebleau GPUs. So all the GPUs can be profiled with VTune. And GPU off-road cost profiling is available. So CPU and GPU boundness you can analyze, and also you can measure the off-road overhead and host-to-device traffic and GPU compute versus data traffic. And also you can measure the GPU utilization and software queue. So once you are done with GPU off-road cost analysis, you may focus on the GPU hotspot analysis. In this case, you can see the XPE. XPE is acronym of XE Vector Engine, which is somewhat similar to SM from the NVIDIA side. So XPE and the memory efficiency metrics you can see, and GPU occupancy limiting factors you can identify, and also hotspot analysis provide the memory hierarchy diagram and throughput analysis. So you can see that it's very intuitive interface you can see. And in addition, so up to now we are talking about some kernel-based analysis. But in many cases, the kernel itself is very complicated, and then you may wanna go more finer grain of the analysis than the kernel level, right? In this case, you can do the source level in kernel profiling. For this feature, we have to have some debug symbol to understand the source line. So in this case, you need to build your application with these two flag. So -f debug info for profiling and -g line table only. You can also build your application with -g flag, but sometimes -g has too many information, so your executable binary could be gigantic with -g. So in this case, so for the profiling, we don't need to have all the information from -g flag. So because of that, this is a kind of alternatively suggested the flag, which is lightweight than the -g, and then provide all the required information for the source line analysis. So once you build your application with these two flags, you can run your VTune for the dynamic instruction count analysis. In this case, you can see how many instructions executed per line based, and also basic block execution latency and memory latency. You may see if you see very high memory store ratio, you can run it, and then you can see which line spend most of the memory latency, and then also store sampling analysis and memory access pattern analysis. So okay, there is one question in the chat. So Alfred asked, just curious if Intel VTune Advisor have large overhead not recommended for Aurora. Why are we talking about them? So I'm not saying advisor V-tune and advisors are not recommended on Aurora. We are recommended to use Aurora on Aurora. The thing is, at large scale, if you want to see you may want to see run your application in the 20% of system, which is 2000 node case, right? So in this case, you can still run with the V-tune and advisor. But the advisor V-tune collects so much data. So if you run with the old MPI rank in 2000 node case, your collected data will be really gigantic. And then in general, what you can see is in general, per MPI, per each MPI, you may expect your kernel execution could be pretty similar to each other, right? So if so, instead of profiling every MPI rank with V-tune advisor, you may just attach MPI V-tune advisor to the specific set, a subset of the MPI rank to the subset of MPI rank, and then do the analysis and then see those data, and then you may expect what happened in your kernel, right? But that is for kernel-based analysis or source line-based analysis. But if you are just running okay with several, so if you are confident about your code is fully optimized for the GPU and CPU usage, right? And then when you scale out your application, you may see weird performance loss happen, right? In this case, B-tune analysis is kind of the kernel optimization. So kernel optimization is not required in this scenario, right? And then still you can run the B-tune, but it's very high overhead. So for that scale, and then some issue at scale, you may just need to get some required MPI traffic data or some network traffic data, not the kernel-based data, right? So in this case, APS is required. So that is what I'm saying. So at scale analysis, APS is the good tool for that. And then for kernel level analysis, still advisor and B-tunes are very useful. So does it make sense, Alfred? Okay, got it. Okay, so on the B-tune analysis, there are a lot of features, but I would like to introduce the 3 features. So HPC performance characterization. So this is kind of the first step of B-tune analysis. So it provides a different aspect of the application performance. For example, high-level hardware information and CPU core utilization, GPU stack utilization, including XP hardware metric and top offload region, and CPU side memory metric, and the CPU instruction. So basically, HPC performance analysis is to see what happened on the CPU side and GPU side together. And you want to see, and after looking at that, and then if you see CPU side, you have a lot of stall happen, a lot of issue happen, you may need to go into the CPU analysis more, right? And then if you see the GPU part is kind of slowed down and GPU has very low utilization, you may need to go into the GPU analysis, right? So this is kind of first step for the analysis. And then once you see CPU part is okay, and then, okay, GPU part, I need to go deeper. You may want to see what is GPU offload overhead, right? Possibly data transfer and kernel launching, etc., right? So in this case, GPU offload analysis could be another next feature you can investigate. So it provides the study of the application offload implementation and assesses its efficiency. So trace level 01 OpenCL API function in one API software stack, and then detect long latency host function, or showing some time spent in data allocation and transfer function, as well as kernel device time. So in this analysis, you mainly working on what could be the text for the data GPU offloading. So sometimes at the very frequent mistake happen at the very first day of the GPU computation is your GPU kernel is really fast, but you have so many synchronization between CPU and GPU, or so many unnecessary data transfer between CPU and GPU because of latency. Your overall performance just become very bad compared to CPU side, right? That is the first or very frequently happen the mistake, right? In order to identify those kind of issues, GPU offload analysis is a good feature to detect that issue. And then once you're confident about, okay, my GPU offload overhead is small enough, and then if you may want to go more deeper in the GPU kernel optimization, right? In that case, GPU compute media hotspot analysis is the feature you can try it out. So this is most accurate analysis in tracing kernel and GPU. And it allows to analyze most time-consuming GPU kernels and characterize GPU usage based on GPU hardware metrics. It collects a set of the GPU metrics in the sampling frequency. So it actually collects a lot of the data for your GPU kernel. So you can identify the performance issues caused by memory latency or inefficient kernel algorithm, or you can also analyze GPU instruction frequency per certain instruction type. So this is one of my favorite because at this stage we have a lot of application. We ported several important application to Aurora system, and then now we are pretty confident about the GPU offload cost is kind of okay or negligible. And now we are working on what could be hotspot of the GPU and why this hotspot spends so much time or so high storage ratio, etc. In this case, GPU hotspot analysis is the correct features we can investigate. So as you can see here, in the summary page, you can see what could be the hotspot and how much time is used and what is the SIMD width and the local size and peak occupancy, etc. Right? And also, if you go to the graphs here, you can see the memory hierarchy diagram, and then you can intuitively see how much data transfer happened, what is bandwidth between the L3 and SLM and the LLC and etc. PCIe and etc. Right? So, and also if you click the graph and the platform tab, you can see the time series of all different metrics, so GPU engine usage or the GPU compute thread and etc. Right? So you can see all the thing in here. So I have example later, so we can discuss a little bit more. Okay, so as you can see here, the P-tune has a lot of the GUI interface here, right? So what could be the best way to use this P-tune GUI interface? Again, you can collect, you can see the data and everything in the table and the standard output, but it's not very intuitive, right? So in order to, a very naive way to enable the GUI interface is on the terminal, you just enable X level forwarding, and then you may just type the ptune-GUI, and then the ptune GUI interface will be popping up. But after doing that, you may realize that the latency is really, really high. So it takes too much time just to load the data. And if you click something else, you may just wait a half minute or a couple of minutes to load the next page, right? So this is really inconvenient and not productive. So alternative way could be you can download the collected data to your local laptop, and then you may install your the Python client version on your local laptop and then open it up, right? There could be a way, but it also has limitations. So as you can see here, Python have many different features. So I'd say Python, the way to use Python is kind of the progressive optimization, measurement and optimization. So after running one case, and then you may find out another case, and then you may go deeper with another additional knobs, right? So you have to run a series of the Python to identify the issue and optimize your code. So in this process, downloading every case and then running them, that also takes a lot of time, right? So our recommendation is just to use the Python server for free collected result through the SSH terminal. So what you can do is you just need to open the terminal and then log into the Aurora login node. X11 is not required. So as usual, you can do the SSH and Bastion and then SSH and Aurora. So once you're Aurora login node, you need to load one API module. So you can skip that because as a default, one API module is loaded. So you can skip this one, and then you just need to type btune-backend and -- data directory is equal to some location. So if you're a Flare project space, you need to put the rooster Flare and project name and some specific collection name, right? So I can show you later. So once you type this btune backend line, you will see the IP address with some port like 127.0.0.1 and then some port number printed by Python backend, right? So once you get that, you need to open another new terminal, and then you need to establish SSH forwarding. So SSH-L, and you need to copy and paste this the IP address with port number twice with the colon, and then username and bastion. And once you're on the bastion, you need to do the exactly same thing on the Aurora node, right? So once you do that, you establish SSH forwarding, and once you do that, you just need to copy this IP address to the Firefox browser. So I tried Chrome and the Safari or something else, but nothing works. So Firefox works fine. So you need to install the Firefox and then copy that address with the port number, and you will see some warning about some security, but you can trust us. And then once you advance, you can see this Python GUI interface. So I will show you after that. So yeah, Alfred, we will share this slide after this this webinar, so you can follow up the instruction. Okay, so that's Python features and Python the server backend, the server the configuration. And again, the APS is kind of the hierarchy is weird because APS is part of the Python. So whenever you install the Python, APS is in it. So, but in order to run it, you need to call it APS, not the Python. So basically, the full name is Python Profiler Application Performance Snapshot. So it provides aggregated view of application at scale, designed for large MPI workload. So it captures performance aspect compute intensive application, mostly about the MPI, OpenMP usage, and imbalance, memory MPI imbalance, and also CPU and GPU utilization, some required basic metrics, and the CPU storage due to memory access, vectorization, I/O, and memory footprint. So in order to run the APS, you need to do MPI run or MPI XAC, and -n and MPI number and MPI rank, and then you may put the PPN 12 and the GPU tile compact script for the GPU finally. And then you need to add APS -r. -r is for the result folder. Then just put the result folder name, and then your application and application parameter. So that's all. And then it will run it, and then it will just finalize that. And once you're done on the login node, back to the login node, and then just type the APS-report and then result folder, and you can see the data. And it also generates some HTML file for the aggregated summary, the information like this one. So you can see here the CPU time, GPU time, and the instruction per cycle, and GPU stack utilization, MPI time, etc. This is a summary page, and then using the CLI command line interface, you can see more detailed data for especially for the network traffic and MPI traffic, etc. So this is another tool you need to keep in mind when you have some issue with the scalability with many nodes. Try it out the APS instead of Python Advisor. So APS, the question is, does APS require specific compilation option? No. APS just use the required limited hardware counters and then MPI metrics, so you don't have to build your application again. Even Python works fine without that, but if you want to do the source line analysis part, some features, you need to do that. So otherwise, you can just run it without any special flag with the APS and Python. But that's a good question though. Okay, so this is APS instruction, and then advisor. So advisor is one of my favorite tool. So this is so advisor and Python are different. So APS is part of the Python product. So you can say, someone may say APS is part of Python, just Python, but because it is inside of the Python package. But advisor is for a different package. So people usually confuse advisor and Python. So someone say Python refined feature that doesn't exist. Someone say advisor hotspot analysis, it doesn't exist. So advisor is more likely, Python is more likely progressive optimization and profiling, right? But as I said, so it has a lot of different features. So you start from some basic analysis, and then you go deeper and deeper and deeper depending on what you see on the results, right? But the advisor has a different approach. The advisor has a pre-selected set of the metrics, and then it just collect all the metrics required by advisor, and then it just provide and then just finalize and provide the final result, and then provide some advice sometimes it's correct, sometimes it's not correct, but that's a different approach, right? So if you run some same workload, for example, if you're running some application, for example, AMR wind application with some specific geometry, if you run it on Btune case, you may need to run multiple times with Btune because at every analysis you may see some difference, right? And then you may decide another knobs to investigate additional issues, right? But the advisor side, you just need to run one times with advisor, and the advisor will collect pre-selected metric and then provide whatever they found out, right? So it's more like a design tool, and then also analyze performance of the CPU and efficiency on GPU float, and also some flow graph design and analysis. And you can see the CPU replying and GPU replying together, and then also see some overall summary of CPU and GPU analysis, and also hotspot on the CPU and GPU side. And if you go to roofline analysis on GPU side, you can see a lot of that. That means it's aggregated per kernels. And then if you double click one of the kernel, it also expand kernel same kernel, but different workgroup size, right? So you may see what kind of the variation happen even in the same kernel. So this kernel with a very small workload has very low efficiency, but this kernel with very high workgroup size has very high efficiency, something like that, right? This kind of variation happens. So it's very intuitive and very effective way to understand what happened in your application. So in order to advisor, you need to follow this instruction. So advisor version, the latest version, yesterday we have the compute image update. So we have the latest version on the default one is the latest version. So if you use the default one API module, the advisor version is okay. So Yasi answered you a little bit accurately. So Yasi said you have to build your application with -G, and then to get the Btune result, there are different command. But that is not actually required. So -G or the debug symbol is not required. But some specific source line analysis, instruction count analysis, you need to use that debug symbol. So the answer is yes and no, right? So I just want to clarify anything. So let me know if you have additional question about the build. Okay, so advisor version is 24.2.1 version, which is the currently latest version. And module load one API is not required because as a default, you have the loaded one API module. And then you need to set the project space where you want to save your result on the space, right? And then there are two ways to run the advisor. So what first way is if you just run your application without MPI, we usually use MPI, but in some case, maybe some micro benchmark or very small workload size. In this case, you just need to type advisor, collect roofline, and dash profile GPU and project directory, and then run your application. So in this case, advisor run your application twice, so automatically, and then collect all the required data. But if you use MPI EXEC, most of you do that, right? If you use MPI EXEC, you need to run this command line, which is requires survey analysis and tree count analysis independently. So first run should be MPI and -N GPU tile. So in this example, I just use two MPI rank case, and then I just attach advisor to the first MPI rank. So and using the MPMD mode, multi-program, multi-data mode. So MPI EXEC-N, GPU tile compact, this is common, and then advisor, collect, survey, GPU tile, profile GPU, and project DIL, and then your application. And then with colon and -N1, or if you run the 12 MPI rank, you can put the -N11, right? So -N11, whatever remaining number of MPI rank, and the GPU tile compact, and run your application. In this case, you're just running advisor to attach it to the first MPI rank, right? So in this case, you assume all the MPI rank to the similar type of the computation, right? And then once you're done this survey analysis, you need to run MPI run -N GPU tile compact advisor and collect trip count analysis again. And the profile GPU, that's just plop and no trip count. It's something weird, but anyway, you can just copy and paste it here. And then, so just run the trip count analysis to the first rank again, and then run other MPI rank without the advisor, right? So once you're done, you can just type the advisor on login node or compute node anywhere. So advisor report all project directory and then report output and this one, and you can get the one HTML file. So this is pretty handy. So you don't have to install advisor client or client on your local machine. Instead, you just download HTML file to your local laptop and then just open it up, or your iPad or your phone. I never tried phone, but anyway. So you can open it up, and then this is kind of the fat HTML. So it also has some native the GUI interface. You can then click and move on, and then you can see the tooltips and etc. You can try it out later. Or if you really want, you can just download the project folder to your laptop and then open it up with the advisor client version. So yeah, that's the instruction. And the last one is TAPI, tracing heterogeneous API. It's very lightweight tool. I think this is most popular tool among the Aurora users. So TAPI is portable. So if you use TAPI, you can expect it can run on OpenCL level 0, CUDA, HEAP, OMPT, and MPI. So it provides some tracing of kernel, and also it provides sampling data for the power, energy, power, and other some memory metrics, etc. And also it has a pretty visualization feature using Perpetual. So if you use Perpetual, you can also see what kind of the kernel launching happen in the timeline. So this is pretty simple. So this is a kind of overall, I mean, the overview of the vTune Advisor, APS, and TAPI. Any question? Are you still with me?
Yeah,
Okay.
I just saw one question, JaeHyuk.
If there are MPI, yeah, okay. If there are MPI, multiple MPI, how can I do that? So, so there are multiple MPI. You can just run it with the advisor and vTune and everything, right? So again, here, as you can see here, using MPI, you can just run with vTune for all the MPI. So in this case, what you need to know is all the MPI rank will collect the hardware metric, right? That means you are collecting a lot of data. And then if you're running the similar workload at every MPI, so if you are doing the adaptive mesh refinement, you can expect your computing per MPI rank could be different, right? But in general, if you are just running the similar kind of workload for MPI rank, you can just attach one of the MPI with the advisor or vTune, and then you may just see that in this case you can reduce the collected data size, and then you can avoid the really high overhead over there, right? And then if you're running really at scale, say for example more than 100 node or 1,000 node, in this case we highly recommend use APS to understand what happened with your application at scale, right? So that's my answer, but I don't know I answer for your question or not. So if not, please add additional questions. Chang. And also I've read it for advisor, yeah, same thing here, right? So in this example, I just attach the advisor to the first rank, and then other rank I just run without the advisor, right? So you can do that. Also, you can run the all different advisor, and advisor created the multiple result folder with the different the different node, right? So either way is fine. Can I select a specific MPI rank just for advisor? Yes, this is the way, right? MPI the NPMD mode. So I attach it here first the 0, but you can using the NPMD mode, you can attach advisor to the specific the MPI rank. And Alfred said if you sample a subset of the MPI rank, will it affect load balancing and throw off a vTune and advisor? So that's a really good question. So usually depending on the advisor the vTune feature, right? So in the runtime, there are two types of overhead. On the vTune case, overhead during the runtime. So if you do the hardware metric collection and then if you don't use really small sampling period, so if you just use the default sampling period, runtime overhead of VTune is okay. I don't think you will see a lot of load imbalance. There may be a lot of load imbalance. So in general, we can say the overhead could be around 5% or less than that, right? So in runtime overhead is okay. So it doesn't require a lot of load imbalance. It depends, right? If your application is really sensitive to the load imbalance, it may create some load imbalance. But in general, I can say you don't need to worry about that too much. But another overhead is once you finish the collection, there is another process to finalize your data. So finalized data is your application execution is completed already, so it doesn't affect your application performance, right? But the finalization process is kind of proportional to how much data you're collected, right? So because of that, again, still, if you attach to subset of MPI rank, you can reduce the amount of collected data, and then you can reduce the finalization overhead. Another thing is if you do the source sign analysis, for example, instruction count analysis or some other latency analysis, in this case, the VTune use instrumentation-based analysis. In this case, runtime overhead is pretty high. So in this case, yeah, load imbalance can happen, but still, the reason you're doing that is you want to count how many instructions happen, something like that, right? So yeah, load imbalance wise, it can, I mean, change the situation, but other side is still valid information. So I don't know the answer for your question, Fred. Okay.
Yes, thank you.
Okay. And Junyi, yes, we will send out the slide after this webinar, so you can get this instruction after that. Okay.
Okay, thank you.
Any other question? Okay, if not, we just have 20 minutes. So let me give you some simple example case here, right? So here, oh, I lost the compute. Let me log into the system. Okay, I'm Aurora here. So let me try to grab a node, okay? So while we are waiting, we already have the one API module loaded as the default, right? So what you have now is 24.07.30.002. This image was updated yesterday. So if you build your application before yesterday, you probably need to build your application again because there is some issue between the new image, right? So anyway, advisor version we have is 24.2.1 version, and advisor health. If you type that, advisor health, you can see collection and the report and snapshot, right? And advisor collect, you can see all different the parameters. So there are so many different flags here. So you can just follow my instruction to start, but if you need more analysis, for example, the sampling factor or so you need to check the advisor health to collect, right? So in VTune case, again, VTune help is again 24.2.1 version we have, and then VTune health, you can see the different the actions, collect and also report and finalize, right? And then VTune help, collect, and GPU hotspot. You can see or additional flag you need to use if you want, right? So that's that. And then let me show you how to establish VTune backend. Okay, so I had pre-collected data here. So this is my pre-collected data here for this webinar. So what I need to do is btune backend, right? Dash dash data directory equal to the folder you want to see. And if you run it, it shows, okay, btune profile GUI is accessible through HTTPS 127.0.0.1 and colon 342339. This is a kind of a dedicated port assigned to me, right? And then what I need to do is I need to get another terminal, and then I need to SSH, and then instead of dash y, just put the dash L. This is to establish SSH forwarding. So SSH-L, this IP address twice with colon, and then run to my Aurora account. Then now I'm on the login node, right? That means you don't see anything different, but that means it is established. And then you can copy. And then I have Firefox. So I lost the previous connection here. So here, so if I just copy and paste it here, you can see potential security risk ahead. Okay, I trust the Aurora system, so advance and then accept the risk and continue. And then btune interface is popping up, right? And here in that folder, you can see several pre-collected data here. So if I open it up, the HPC performance analysis here, it takes a little bit time, but compared to X11 forwarding, it's much better. So it's popping up. So you can see the result very soon, I believe. Okay, so here you can see this is HPC analysis. You can see CPU time, GPU time. This is a very simple benchmark doing nothing, so you don't see any meaningful data here, but I just want to show you the skeleton of the result. So you can see the socket 0, socket 1, CPU side, HBM, and DRAM, and etc. Right? And then you can also go to bottom of process and then see the results. So let me quickly move on what I have here. So HPC performance analysis, what I did was MPI EXEC-N12, PPN12, GPU type compact. This is a general MPI command line, right? And then I added the red part. The red part is required for the btune. The btune collect HPC performance and dash out btune. This is the result for the btune HPC performance result folder. And then this is application name, and then the some parameter per application. So as you saw before, you can see the overview of the platform diagram to dual socket. So HPC performance analysis is for the CPU and GPU, both of them. You want to identify which component, which part has some problematic, right? So it shows both of them, and also shows GPU stack utilization. In this case, 0.7% is pretty low, right? Something wrong because I'm just running a simple benchmark with nothing. So it is why I get no. But in real application, if you get the 0.7%, you have to dig into what happened in your GPU source. So, and then memory bound and vectorization, and also on the bottom of platform, you can see the core stacks, and then what happened on the GPU side, and then what kind of the metric happened, right? So this is kind of the very general overview from CPU and GPU both sides. And then let's say, okay, we see the GPU stack utilization is pretty low, so I want to check why it happened. Maybe this is because of the offload cost. So in this case, I ran the GPU offload analysis. So only difference is I changed it to the collect GPU offline instead of HPC performance. So when I ran it, I got this analysis, and then it shows the per GPU. We have 6 GPU, and each GPU has 2 stacks, right? You can see all the GPU listed in here, and then the GPU time is pretty low here. And this page is interesting because when you go to graphics, you can see what happened in the GPU, 6 GPUs, right? GPU 0, 1, 2, 3, 4, 5, right? I just expand GPU 4 and then expand GPU stack 1. And here, the comp geo, this is the only kernel in this benchmark. You can see it spans 93 millisecond, and then you can see that this is the green part is host to device transfer, pretty short. and yellow part is execution, GPU execution part. It's longer than the green, but shorter than blue. And blue part is device to host transfer, device host to transfer blue. So from this analysis, we can see we have very little computation happen here, and then most of the time used by the device to host transfer, right? So that is very obvious because this is simple benchmark with very limited computation. But in real application, if you see this one, that means you have some problem between in the offload overhead, not actual GPU kernel computation, right? So in this case, you need to modify your data synchronization or data transfer between host and device. So from this case, you can get the hint, right? And then also again, if you go to platform folder, you can see all the different metrics: GPU compute, traffic, memory access, stack to stack access, etc. So you can see this metric. So you can identify how much offload cost you have, and that is reasonable or not. And then you can decide where you go, right? And then let's assume, okay, offload cost we figured out, and then we want to look into what happened in GPU side. In this case, you need to run with the GPU hotspot analysis here. So MPI run, and then ptune collect GPU hotspot, and share the result folder, and then run your application. So again, you can see what kind of the XPE active idle store happen in this for all the GPUs and different stacks. And then if you go to graph and the memory hierarchy pane, you can see a very intuitive diagram. So this is your Xe core, and then this is L3 core, L3 cache of your GPU core, and then this is HBM of GPU core. And then outside of HBM is PCIe traffic between the host and device, and then LLC on the CPU side, and there is another the memory on the CPU side here. So from here, from this diagram, you can see how much bandwidth your application get between each level of cache and inside of your Xe core, and you can also choose different GPU and different stacks and see what's going on over here. And again, if you go to graph and the platform, the pane, you can see also the time series. And then if you move around your kernel, you can also see the tooltip popping up and showing the actual the data from that time point. Okay, and you can also choose the different GPUs here. Okay, so up to here, you don't have to build your application with additional flag. You don't have to. You can just run it whatever you have, right? Because everything is kernel-based analysis. But let's assume you identify one of hotspot kernel. For example, there's some smooth kernel spend most of time and very low XPE active ratio, and it is problematic. So you want to include that. You want to optimize that kernel. In this case, you may want to know what is the line by line based performance of this kernel, right? For this analysis, you have to build your application again with the debug symbol. Again, -G is workable, but -G maybe include too much information. So another alternative way is, as I mentioned at the beginning, the -G line and also -G debug. These two flag is more lightweight than the -G, and then still provide the same information. Okay, so for this analysis, first of all, the between instruction count analysis, I want to know how many instructions are executed per line based, right? So for this analysis, you have to build your application again with that debug symbol, but the others you don't have to do, okay? So if you do that, this is very simple kernel. So you can see each line of so this is only GPU kernel, this is CPU part, right? So GPU kernel, how many instructions executed per line? So you can see this for loop has a lot of instruction for the control floor. And then this line has FMA instructions. So you can see the double precision integer 64 TP floor instruction happen, right? This is really makes sense, right? So here, this is a very simple benchmark. So each for loop, we just have a single FMA, but in general, you have much more computation for the for loop, right? So in this case, this control flow overhead could be kind of the negligible, and you will have a lot of instruction inside of the for loop, right? So this kind of will happen. But again, with this instruction count analysis, you can actually see how many instructions are executed per line based, and then you may have idea, okay, this line is very problematic, it spent a lot of instruction, it's not expected, something like that, right? And also, you may want to know okay, before going to instruction, I just want to see how many cycles are consumed per line, right? So in this case, you can just run the source line analysis. So for that, you need to add a knob profile mode source line source analysis, and then you can see this line-based analysis. So here, what it's saying is the 3.9% of time out of the entire compute time used by this for loop, and then to initiate this for loop, and then actually 4.3% of time used by this execute this FMA instruction, right? So again, this is a simple benchmark. This is kind of distorted, but real application, you may see a lot of different variations, and then you may see, oh, I didn't expect this line spend so much time, but actually this line spend a lot of cycles. I need to figure it out why, right? So this kind of analysis can the measurement you can see with source analysis. And again, if you have a very high store ratio on your kernel-based analysis, and then you may want to know why this kernel has so high store ratio, why memory operations store very a lot. So in this case, you can also run with the memory latency analysis again with the debug symbol, and then you can see, okay, so this line has a lot of memory access, memory instruction happen, and then the memory latency is 770 cycle for this line, right? So, and then you may realize that this is kind of reasonable and this is not make sense, and then you can move on, right? So this is kind of the deeper analysis required the debug symbol. And then APS side, again, I just ran application with a 16 node case as an example. So MPI run and 192 GPU type compact, and I just added APS-R and then this number, and then run the application, and it shows what is the CPU time, GPU time, and also GPU stack utilization, MPI time, and physical time, right? And also, this is kind of the summary HTML file. It does not have a lot of GUI interface from the APS, unfortunately. Instead, APS still collected pretty good set of the data to understand your performance. So if you go to APS GUI, APS command line interface, you can see more data. So in order to see what kind of metrics are available, you can just type APS report -- metric is equal to question mark. And then this is kind of the APS result folder. So if you type that, it will show what kind of the metrics are available here, right? So here, MPI time or MPI wait all, or MPI ISAN, all reduce is required, something like that, right? Or you may be interested in the network controller inbound PCIe read or write, or outbound read or write, or maybe GPU inbound PCIe read or write, right? So this is mostly about the communication, because this is a performance measurement for scale, right? So as an example, I just typed the APS report and then the APS result folder, and then metric, MPI time, and GPU occupancy. So once I type that, you can see, oh, MPI time for this node, MPI rank 135, spend 30 seconds. And then this node 167 spent 29 seconds. So if you have some memory MPI imbalance, you can see big variation, right? So some specific MPI rank spend 100 seconds, some MPI rank spend just 10 seconds, and you can see the memory imbalance is pretty severe in the case, right? And also GPU occupancy per node is around 54%, etc. Right? So again, by adding additional metrics in here from this list, you can see additional text data from the APS collection. And advisor offline feature again. So I just ran it on single node with 12 MPI rank, and I attached the advisor to the first MPI rank. So I just run the MPI-N1 and then advisor, and then the :-N11. So remaining 11 MPI rank just running without advisor. So in this result, I could get the result for the first MPI rank result, and then this is just one single the kernels you can see on the 1 point. But as I showed you in the previous slide, you can in real application you can see a lot of different dots, and also you can see you can expand them per the workload size. And also advisor provide what is the memory metrics and instruction mixes, instruction mix details, and then some performance characterization, right? So it's kind of the one-stop analysis and see what's going on over there. So, and the TAPI, okay, again, in order to use TAPI, you just need to model load the TAPI, and then the MPI run, PPN, and then I just added iprop, so you don't even specify what is the result folder. and then I just run it, and then it just print out. It just provide the pretty nice the information in the standard output data output mode. So here it provide the MPI backend, so how much time used the MPI INIT finalization reduce, and also OpenMP backend use OpenMP function, level 0 backend, level 0 function, and also the device profiling, how much data transfer between host and device, and the memory access pattern from the MPI, OpenMP, and the level 0, right? So since the overhead of iProf is pretty negligible, so it's very popular among the Aurora users. So, and okay, this is my last page. So with the latest SDK, there are two known issues. So first issue is you may get the following errors at the end. So exception, flag fault, and then module lib sweep.so. So we already know this issue, and we have workaround. So before running advisor between APS, you just need to run this export sweep null socket is equal to 1. Once you add it on the compute node, you won't see that issue. And 25.0 version will have that fixed, so you don't need to worry about that with the next version. Another symptom is after finishing the collection, Pigeon say error cannot stop collection of GPU event. So it's very weird error, and then it turns out it's a false alarm. So you can just ignore that, even though it says error. Intel is investigating the issue, but at the moment you can just ignore that, and you can still open it up your result without any issue. So if you have any other issue, feel free to send the email to support@anl.gov or myself, and we can help you out for any other issue. So that's all I have, and I think we just have 1 minute. Any other question?
Thanks, JaeHyuk, and thank you, everyone. So if there are any questions, that would be the time to ask. And I guess if you do have access to Aurora, you can try it. Can they also try it on the Intel Developer Cloud, JaeHyuk, if they have access to that?
Yeah, Intel Developer Cloud is a good platform. You can try it out if you don't have access to Aurora, right? But the only limitation is advisor APS, everything should work, but only limitation is the Developer Cloud does not have any capability to port forwarding, so Beacon backend is not available. So in this case, you have to download your folder to your local laptop and then open it up with your client version. So other than that, Python Developer Cloud is still a pretty solid platform to try it out.
And I want to point out that we will distribute the slides and as well as recording.
Yep.
And it also will be added to the website, so you will have access at it at any time. Will we be able to apply for access to Aurora? When Aurora becomes public and you'll send a lot of emails about it, then yes, you would. At this time, it is still restricted access.
But it will happen pretty soon, right?